I want both of you to work on this project on geometric extremas.
Challenge accepted!
For this circle centered at 3, 4, the modulus extrema occur along the line y equals to 4 over 3x, passing through the origin. By adding and subtracting the radius of 2 from the center's distance of 5, we find z minimum is 3 and z maximum is 7. For argument extrema, we set the discriminant to 0, finding tangent lines with slopes of 0.57 and 4.3, giving us an angular range between 29.7 degrees and 76.7 degrees.
Geogebra timing!
To justify the modulus z minimum and the modulus z maximum, I created two circles centered at the origin. For the inner circle, I showed that when the radius of a circle from the origin is exactly r equals to modulus z minimum, it just touches the locus at the nearest point, which is 1.8, 2.4. For the outer circle, it's perfectly inscribed within it, touching at the furthest point, which is 4.2516. We can see that this point falls perfectly on the straight line, y equals to 4x over 3. To justify the minimum and the maximum argument, we use y equals to 4x over 3, and we can see that m max is equals to 4.23, which is the argument maximum point, and the m minimum is 0.57, which is the argument minimum point.
I think both of our methods are correct.
Yeah, we're so good.
Let's go.
Now it's my turn to investigate. Since Tzen Yuan used Geogebra, I should follow in his footsteps. Now we have to calculate for the argument extrema. So what we have to do is to substitute in y equals mx into our general ellipse formula, and then after that we're going to convert it into a standard form.
Wait a minute!
So we have the general equation for the complex loci. There's three values that I have to substitute in. To keep it simple, we're going to use these values. So what we're going to do is to use isolate and square method both times in order to convert it into a general form. So what this does is to convert from imaginary form to Cartesian form so that we can easily represent it in an xy plane. Now from the standard form, we can actually set the discriminant. So the discriminant just tells us like how many roots a given quadratic equation have. We only want one root, which is coincidentally the tangential formula. So after we set the discriminant to 0, we can just easily solve for m, and we're going to get two answers, m equals to 1 and -1. So we can make two linear equations from that. And from the two linear equations, we can actually just solve for x, and after that we can just substitute everything in, and we get the complex number. So for the modulus extrema, because I chose my focus to lie on the real number line, I can just substitute z with x and we can just solve for x. So we get x equals to 12 and x equals to 2. After that, from the general quadratic form that I solved for just now, I can represent y squared in terms of x, and then we will shove this into the distance formula. The distance formula is just another way of writing a circle. If we plug in the x values that we get respectively the minima and maxima at 2 and 12 on the real number line.
I see. How about we use my calculation method? And for the ellipse, with this equation, the modulus extrema occur at the vertices along the major axis. By calculating the distance from the origin to the horizontal bounds, we find the minimum modulus is 2 and the maximum modulus is 12. And to find the argument extrema, we substitute y equals to mx into the ellipse equation and set the discriminant to 0 to find the tangent lines. This calculation simplifies to m squared equals to 1, giving us slopes of 1 and -1. Consequently, the maximum argument is 45 degrees and the minimum is -45 degrees.
We